Swayam Prabha. Digital India. Educated India.
Now we'll look at another theorem which can be considered the dual of the Thevenin's theorem. It is known as Norton's theorem. Just like Thevenin's theorem gave us a representation of a complicated circuit at two terminals with a single voltage source and a single series resistance, Norton's theorem will also give us an equivalent circuit at two terminals which consists of a single current source and a single resistance in parallel. Okay. And the derivation of this equivalent is similar to the derivation of the Thevenin's equivalent. Okay. So, let us say we have a network N consisting of independent sources. I will show them by a single source like this, resistors and linear control sources, and it is connected to some other circuit. Okay. Let me call this my circuit. Now, what we wanted was a representation of this circuit N at the terminals 1 and 1 prime. So, it can be a stand-in for this circuit regardless of what you connect to it. Now, if you recall, while deriving Thevenin's equivalent, we replace this with a current source based on substitution theorem. What we will do here instead is, let me again say this voltage happens to be VL and this current is IL. I will replace it with a voltage source instead. Okay. So, I will substitute this whole thing by the voltage source whose value is the voltage that actually occurs in the circuit VL. As before, we see that the derivation will be independent of whatever VL is. So, it applies to any circuit, okay, anything that you connect. Again, this is the circuit for which we are computing the equivalent, and this circuit needs to have only independent sources, linear resistors and linear control sources. This can be anything, it does not matter what it is, okay, because whatever it is, between these two terminals, it can be substituted by a voltage or current source of that specific value, whatever voltage or current it is drawing. And finally, whatever we are going to derive for this, the equivalent for this will be independent of the value of VL. Okay. So, let us take this and proceed as before. Now, let us say I were given this circuit and asked to compute IL. Now, there are independent sources inside and there is one independent source outside, which is VL. Okay. How would I go about solving for IL? I could use superposition. I can think of this as superposition of two cases. I will indicate a plus here to indicate superposition. And what are the two cases? One in which the internal sources are active and VL is set to 0. That is, VL is replaced by a short circuit. I will compute IL 1. Okay. And the other case is where the internal independent sources are all nulled or deactivated. I will have only this VL to be active and I compute IL 2. My IL in the original case would be the sum of these two cases IL 1 plus IL 2. Basically, I have these independent sources VL and all of the internal independent sources. In one case, I activate all the internal independent sources, but null VL, and in the other case, I deactivate all of the independent sources and activate only VL. Okay. Now, let us go step by step. What is this? In this case, what I have done is to have all the internal independent sources to be active. Okay. So, these are all active, and I terminate the output or these terminals 1 and 1 prime, where I want to find the equivalent with a short circuit. Okay. Because when I set VL equal to 0, that is what I get. I have a short circuit and I measure the current through that short circuit. Okay. Here I called it IL 1, but this is usually called IN, the Norton current. Okay. It is the Norton current or the short circuit current. Okay. So, I terminate 1 prime with a short circuit and measure the current in the short circuit in the right direction, okay, going from 1 to 1 prime. That gives me the short circuit current or the Norton current. Okay. And let me look at the second case, where all the internal sources are nulled. Right, all the internal sources are nulled, independent sources are nulled. We have only linear resistors and linear control sources, and we know that such a network consisting of linear resistors and linear control sources looks like a resistor from these two terminals. Okay. And I am considering the case with this nulled, and looking in here, it always looks like some resistor. What it means is that if I applied some V test and measure I test, V test by I test would be some constant which is given by R equivalent. In this particular case, I will call it Rn, the Norton resistance. Okay. So, this is equivalent to having the Norton resistance Rn, okay, and it is driven by this VL, and I am measuring IL2 in that direction. Okay. So, clearly IL2 would be minus VL divided by Rn. Okay. And I have to superpose this with the short circuit current to get the total current. I will do that later. If you recall what we calculated for the Thevenin equivalent, in Thevenin equivalent also there was a resistance RTH. It was exactly the same thing. We deactivated the internal sources and found the resistance looking in. The only difference is there we were applying a current, and here we happen to be applying a voltage, but it does not matter whether you apply a voltage or current, the ratio V test by I test remains exactly the same. So, although I call it Rn just to be consistent with the notation for Norton's equivalent, it is exactly equal to RTH, the Thevenin resistance. The Thevenin resistance and Norton resistance are one and the same thing. Okay. So, now let us go about our superposition. With the full circuit, that is with the independent sources active and we have all the components in place, if we apply VL, we have a certain current IL, and from the two cases that we took for superposition, we know that this IL equals IN, the short circuit current or the Norton current, minus VL divided by RN. Okay. Now, this entire thing can be represented using a simple equivalent. Okay. The current IN, which corresponds to this particular term. Okay. And then I have the voltage VL over there, and to get this term I simply connect a resistance RN. Okay. So, clearly you see that the current flowing here is VL divided by RN, the current flowing that way is IN, the short circuit current. So, the current flowing here is nothing but this current minus that current, which is IN minus VL divided by RN. Okay. This is fine. If you recall, with the Thevenin equivalent, we had got VL to be VTH minus IL times RTH, and we have a similar equation here. There we could emulate the output voltage using a voltage VTH in series with a resistance RTH. Here we emulate the output current IL using a current source IN in parallel with a resistance RN, which also is equal to RTH. Okay. And this particular circuit is the equivalent of this at the terminals 1, 1 prime. Okay. This is 1 and 1 prime, and this is known as Norton's equivalent circuit of the network N. Okay. So, as I said, it is the dual of the Thevenin's equivalent. There we have a voltage source, here we have a current source. Okay. We can state Norton's theorem in a way similar to Thevenin's theorem. Any circuit with independent sources and linear components, that is linear resistors and controlled sources, can be represented at two terminals by a current source in parallel with a resistor. Okay. And what is this current source? This is IN, which is the current flowing in the short circuit between two terminals, and this resistor Rn is nothing but resistance looking into the two terminals with the independent sources deactivated or nulled, that is, they are set to 0. Okay. So, exactly the dual of Thevenin's theorem. Now, the same circuit N can be represented by its Thevenin's equivalent VTh in series with RTh, or by the Norton equivalent which is IN in parallel with RN. RN of course is equal to RTh. Again, the equivalence holds for the circuit between these two. Again, the equivalent holds at these two terminals 1 and 1 prime, and what it means is that if any circuit is connected to these two terminals 1 1 prime, you connect it to either the full circuit or the Thevenin equivalent or the Norton equivalent. The currents and voltages at these terminals will be exactly the same, and consequently, those in the circuit that you connect will also be exactly the same. Okay. So, when you are interested in modeling this circuit, you can either use this or that one. Now, one thing I want to point out is the relationship between the values VTh and IN. These two are also exactly equivalent to each other. That is what it means, right, because this circuit is equivalent to this, which is equivalent to that. So, these two are also equivalent to each other, or the relationship between IN and VTh can be easily found out by considering the open circuit voltage between these two. Okay, because this circuit should also have exactly the same open circuit voltage as this one, if they are to be equivalent. The open circuit voltage in this case, in the Thevenin's case, obviously equals VTh. No current flows through RTh, VTh is the open circuit voltage. In fact, that is the definition of VTh. And in this case, if you do not have anything connected to 1 and 1 prime, all of this IN flows into RN. Okay. So, the voltage across 1 and 1 prime is simply IN times RN or IN times RTh. Okay. So, this is the relationship between the Thevenin voltage and the Norton current of a given circuit. Okay.